Okay, welcome to the morning session, and our first speaker is Alexander Bufetov, who is going to talk. Well, he will announce what the title is, I guess.
Okay, so let me just start, in fact, with the sign process. So we consider the standard sign kernel. And the first result I would like to start with is the following. It is written on the blackboard that just almost every realization of sign process, almost every configuration under the sign process, it's an infinite configuration, is one particle, one, so to speak, extra particle, and then a complete and minimal set for the Pelley-Wiener space. So let us recall just that if I have a, let me even start on the example of Pelley-Wiener space. So the Pelley-Wiener space is the space of functions whose support of the Fourier FNL2 of R, whose support of the Fourier transform is in the minus pi pi, minus pi pi. So all functions in the Pelley-Wiener space are entire, and we can ask ourselves about, and this is a classical question, how these functions are reconstructed, are sampled from their values on a discrete subset of a real line. And the first result in this direction is the Kotelnikov theorem from 1933, so which says that f of t is the sum f k sine pi t minus k pi t minus k, k in z. So this the Kotelnikov theorem is proved just by taking the Fourier transform f hat and representing as a Fourier series and then writing the inverse Fourier transform. So in fact, this is an orthogonal decomposition. This is a series. These terms are orthogonal in L2. In fact, this is a basis. This is an orthonormal basis in Pelley-Wiener space. Orthonormal basis in Pelley-Wiener space. This is not the situation that we will have in our context. So in our context, we will be interested in realizations of the sign process, which are much more complicated, behavior than the set Z. Sometimes they accumulate and sometimes they're very far apart. And in fact, we shall see that precisely also the behavior of the set is different, and which is what the main result is about. Yes?
I'm already a bit lost. You say that the support of f is between minus pi and pi.
In fact, I wrote incorrectly.
Okay.
Excuse me. Yes. Thank you very much. I wrote incorrectly. Thank you very much. I wrote one. Yes. Now good. Yes. Thank you very much. Okay. Yes. So almost every realization of sign process, and this is the theorem of Gauche. Almost every realization of a sign process is a complete set. So I wrote the sign kernel, and I will denote PS, the sign process. So almost every configuration is a complete set for Pelley-Wiener space, is complete for Pelley-Wiener space. So this is a very beautiful theorem of Gauche. In fact, it holds in much greater generality. Such result is true for all determinantal point processes governed by projections, and I will say a few words about this later. Let me recall the definition of complete. So what do I mean by complete here? By complete, I mean that, so for Paul, so I continue with the theorem of Gauche. So for almost every realization X, if a function in restriction to X is zero function in Pelley-Wiener space, if in restriction to x it is 0, then it is in fact identically 0. So, and this is what I mean by completeness. In equivalent terms, the family of reproducing kernels, so please allow me not to write the explicit formulators there, sampled at x in x, is a complete, so spans the whole space, the Pelley-Wiener space. And as I said, this is a general statement for determinantal point process by projections. I will come back to that later. Let me just, for the moment, concentrate on the sign process. So, there are many ways in which a set can be a complete set. So, for one thing, the question, which in fact this result addresses, the question is whether it is a minimal set. What does it mean? Minimal set is a complete set is minimal if no subset of it is minimal. So, a complete set is minimal. So, a complete set. So, this is complete. Is complete. So, a complete set is minimal. Set is minimal if no subset is complete. If no subset is complete. So you remove one point and it is no longer complete. And we shall see that the situation for the sign process, well, as in fact this result shows, the situation for the sign process is that without one particle it becomes complete and minimal. One has to emphasize, and we shall see such example in the second part of the talk, that complete set need not admit a minimal subset. So we are used that a complete basis or a complete family of vectors always admits a basis, but this is not true here. It is quite possible that a set be complete and not admit a minimal subset. We shall see an explicit example very soon. Let me also say that, so one way in which a set can be complete, as for example here, as for example in the Kotelnikov theorem, is when the restriction of the function onto the set. This is just something like small L2. It's just a countable family of values. So this countable family of values is essentially a square integrable function, like here. Here we have just an isomorphism. This is a Hilbert space isomorphism. So nothing like this will take place here. So there is nothing like this here for a very simple reason that, as I said, in fact, the particles quite exceptionally rarely, but they do sometimes accumulate. So there are small intervals which contain very many particles. And in this situation, it is not possible, in such situation, it is not possible for a set to be sampling, because, for a set to be a Riesz basis, so to be similar to a basis. So please allow me not to give formal definitions because precisely I'm just saying that this is not true. So let me not explain to you what is not true. Please allow me to be intuitive here. So just since the particles accumulate, obviously the values of the function are very close at particles, when particles are very close. And this is what prevents it from there being an L2 isomorphism. I should say also that conjecturally, it is possible to take the jet, to take derivative, second derivative, and so on when they accumulate, but such result I don't have. I think it would be very interesting to obtain a result of this type. But this I don't have. So let me just say that there is no L2 isomorphism, no L2 isomorphism. Okay. So before I want to explain also how the argument goes for this example, but before let me continue the following way. Let me consider a different example, and then I will also explain the argument for two very different examples. let me say only that, before I pass to the different example with completely different type of behavior from the sign process, let me just say that still something from the Kotelnikov theorem can be saved. And so there is an interpolation formula. It looks quite different. So taking a configuration X, a configuration on the line. So I can assign to X a random entire function, which is the analog, in fact, in this setting of the characteristic polynomial of the random matrix. This statement can be also made precise. This can be seen as a scaling limit of ratio of values of characteristic polynomial. So here it is, X in X. The product is understood in principal value, so convergence is over symmetric intervals. And this random entire function is well defined for almost every realization of the sign process. So as I say, this is just the analog of the characteristic polynomial for my configuration, which is the scaling limit of eigenvalues of a random matrix. So then the main result is reformulated equivalently in the following terms. So I take X, I take P and Q in X, so two different particles. So, and the statement is that Gx over T of T over T minus P does not belong in L2, whereas Gx, if I remove two multiples from this product, so if I remove one multiple of this product, so this function itself does not belong in L2, and this is, in fact, it follows from the theorem of Gauche. It is not very difficult to show that if it did belong to L2, it would automatically belong to the Pelley-Wiener space. And then, if it did belong to L2 and to the Pelley-Wiener space, it would be a counterexample to the theorem of Gauche. But in fact, so it does not belong to L2. So I can remove one multiple, but still I'm not in L2. And I can remove two multiples, and then I am in L2. So this function is in L2, and this is very explicit in L2, in fact, in Pelley-Wiener space. So this is very explicit example. This is a very explicit example of function that takes value 0 at all particles except 2. Takes value 0 at all particles except 2. Of course, it is now possible. So the set, let me denote it by the set, let me denote xp, so x minus p, is complete and minimal. Complete and minimal. And minimal, okay. So this function I denote by gpx, gpx of t. And then let me write here the analog of the Kotelnikov theorem. Then one does have something which is essentially the Lagrange interpolation formula. One does have f of t is sum over q in x minus p. So gx, so precisely f of q, gxp of t over gxp prime in q. Oh, excuse me, gxp in q, that is okay. Yes, yes, yes. Good, okay. So here we go, but so this sum, so this is essentially just Lagrange interpolation formula. Convergence takes place in any sense you want. But the result, it is obtained in joint work with Alexander Borichev and Alexei Klimenko. So we do need relatively strong assumption on f. The assumption we need is that f times t to the power n, some sufficient large power n, is still in L2. So we do need that the function f decay sufficiently fast at infinity. We don't aim for a precise value, so it seems probable that precise value that we need is something like 3, but we don't prove this, we just say that there exists and not. So just if the function f decays sufficiently fast at infinity, then in fact we show that this series converges. What is the main difficulty? The main difficulty is precisely this denominator. Because when P and Q are very close, it does explode. So this is the main difficulty in our argument. Okay, so this is just the interpolation formula, and again, please observe that in this interpolation formula, again, it can in a quite straightforward way be seen as scaling limit of Lagrange interpolation formula, with the only difference. So let us see, for example, sign processes scaling limit of circular unitary ensembles. But of course, circular unitary ensemble is a configuration, is a measure and configuration of n points. So n points and polynomials are of degree n-1. So n points, a configuration of n points, is a complete and minimal set for polynomials of degree n-1. And of course, there is Lagrange interpolation formula. So this statement is what is taken to the scaling limit, with the difference that, in fact, there is, so to speak, one extra particle, one superfluous particle. So the realization of sign process is not complete and minimal, it is complete and minimal with one extra particle. In fact, so how do I say, the intuitive, the informal reason for this is that this function, so if x were z, then this would be just sine. This would be the sine function. So sine, if you divide by t, we obtain if sine t over t is a function which is in L2. But the random function, because of the central limit theorem of Johansson and Soshnikov, the random function, sometimes it becomes very big. So, and if you divide by t, it's not enough. So this is why. So the randomness destroys, so this, how shall I say, this convergence is destroyed by randomness. The randomness makes this series divergent. This is the point of the theorem. Okay, so this much for this example. So, and now let me consider a completely different example. So a completely different example with completely different results. So, okay, let me start maybe here. So let me consider a very classical example of a determinantal point process, namely the zero set of the Gaussian analytic function. Of the Gaussian analytic function on the disk. So let us briefly recall that that I consider the series some an of omega. Omega is the randomness n with 0, n from 0 to infinity. Z to the n. This is a random series. So an is complex Gaussian, standard complex Gaussian. They're all independent. So, and I consider the zero set. X. Okay, so the radius of convergence of this series is 1. So the zeros belong to the unit disk. And in fact, by the beautiful theorem of Perez and Virag. Perez and Virag. The zeros form a determinantal point process with the Bergmann kernel this one. So Bergmann kernel. Bergmann kernel. Let us recall that the Bergmann kernel is the kernel of the orthogonal projection of L2 on the disk to the Bergmann space, which I denote A2, which is the space A2 of the disk is the space of holomorphic square integrable functions. Holomorphic square integrable functions. It's a square integrable with the usual Lebesgue measure. Square integrable functions. So square integrable with the usual Lebesgue measure. The basis is the usual basis, 1 z square and so on. So the norm of z to the k is 1 over k plus 1, and the series obtains the Bergmann kernel. The Bergmann kernel. And in fact, now we can ask ourselves about the connection, just in the same vein as here. We can ask ourselves about the connection between the zero set of the Gaussian analytic function and the Bergmann space. Okay, so okay, let me continue here. And the Bergmann space. So it is quite straightforward that the Gaussian analytic function itself is not square integrable. In fact, computing the variance, one quickly arrives at the harmonic series, because the variance of z to the n is 1 over n. So it is not square integrable itself. At the same time, this does not preclude the possibility that there exists a square integrable function with zeros at all these points. So it is possible. And in fact, we prove that it doesn't. And this is a result in joint work with Yan Xixiu and Alexander Shamov, both in Marseille, but at different moments of time. So just, in fact, we prove that X is, okay, let me write like this, that almost every X with respect to the Bergmann process, so in other words, corresponding to almost every Gaussian analytical function, almost every X is a uniqueness set for the Bergmann space. Uniqueness set for the Bergmann space. For the Bergmann space. Okay, yes, so this is 2016. Yes, okay, so, but it got published only in 2021, actually. Yes, is a uniqueness set for the Bergmann space. Excuse me, yes, it's the same as saying complete set. Excuse me, complete set, yes. Is complete for the Bergmann space. It's the same thing, is complete for the Bergmann space. Excuse me, I used, this is just equivalent terminology, excuse me, let me stay with what I already used. Thank you very much. Okay, is complete for the Bergmann space. So this result, in fact, our argument does not use the specificity of this problem, the Gaussian analytical functions. In fact, it only uses the determinantal property. In fact, we show this result in full generality for all determinantal processes governed by projections. In fact, completeness holds for all determinantal point processes. Holds for all determinantal point processes. Determinantal point processes. So I should say that this statement has a certain history. It was proved by Lyons in discrete setting in 2014, and this statement was also formulated by Lyons and as a conjecture, and in fact, Gauche proved it under additional assumption, so-called rigidity, which, please allow me not, maybe I will say later as the talk advances, but let me not stop on this right now. So under additional assumption of rigidity, Gauche proved this, but this setting is not rigid, and we proved it in full generality. And let me just say that, as I said, our argument holds for all determinantal point processes. On the other hand, Lyons gave a different proof. Lyons gave a different proof, which is Gaussian. So Gaussian analytic functions may or may not give rise to determinantal point process. So our argument is for all determinantal point process, in particular for this Gaussian analytic function. But Lyons gave a proof specific for Gaussian analytic functions, so which is a different formalism. Yes?
Confused. Don't you have isn't, for instance, the empty set a determinantal point process?
Can you say again?
The empty set, isn't it a certain degenerate determinantal point process?
Corresponding to empty space, to the zero space, so every function is zero.
So I missed what is your... I missed the statement, so I mean...
The statement is that if I have a determinantal point process governed by orthogonal projections, then almost every realization. So let me write it down. So I have a kernel of a projection. Kernel of a projection. So on some subspace, so K projects on some subspace, it's completely general result. So L2 in some space E with some measure mu is projected on some subspace H. Then for almost every realization of the determinantal point process, so if F is in H is 0 in restriction to X, then it is identically 0. Or, you must excuse me, some of this chalk writes really well and some other really doesn't. Sorry, I try to find good chalk. So yes, or equivalently K, this one writes really well. K, X, X in X spans H. So these are equivalent reformulations of the same thing. Okay. So given any projection in any space, given so for example Bergmann space or sign process, but any other also, just almost every realization of these determinantal point processes is uniqueness set for this space. Okay, I missed the fact that the completeness with respect to the image of your projection. That's right. That's correct. Yes, that's precise. Yes? Mm-hmm. Self-adjoint projection? Yes. Emission. Yes, this is emission. So this is a very good question. Absolutely. Thank you very much. This is absolutely a emission result, and in the proof, so here I'm in a situation of difference of opinion with my co-authors. So I think it also holds a non-self-adjoint case, but my co-authors don't agree with me. So we have very specifically, I can show you the line in the paper, where in computing the conditional variance, so how all these, so at the center of the argument lies a statement about triviality of tail sigma algebra, which in turn relies on the fact that variance, if you condition on farther and farther away trajectory, variance goes to 0. So precisely the tail sigma algebra is trivial. And there we specifically use, as I say, I can show you in the paper, I can show you the line. We specifically use the self-adjointness property, and I think it's not, I think we could also get away with that, but as a matter of fact, we didn't.
But maybe in spatial, did you check spatial examples of non-self-adjoint projections.
Like what? What would you have in mind?
I mean,
like
something
Dyson-Brown in motion or something like this?
Or I'm thinking about using multiple orthogonal polynomials or like a
yes, I think this would be. I think this would be.
right.
No, we didn't. I think this would be maybe the best place to start. No, we didn't. No, we didn't. Yes, as you say, by orthogonal ensembles. Yes, yes. I think it's exactly the right thing to do, which we didn't. Yes. Mm-hmm. So, okay. So this is the result. So there is a substantial difference between the case of the disk and the case of the line. There is a substantial difference. In fact, so here, let us look at this. So first of all, it is very useful to note that the zero set, and it is clear from the Perez-Verag theorem, but it is, at least not to me, not clear a priori. So it is useful to consider the unit disk as the Lobachevsky plane, and the distribution of the zero set is invariant under Lobachevsky isometries. So just the action preserves the kernel, preserves the measure, so preserves the distribution of the zero set. Observe that it does not preserve, of course, the distribution of the Gaussian analytic function. So it's just a statement about the zero set. Okay, so this action is mixing and so on. So precisely, there exist arbitrary small disks with arbitrarily many particles. So there exist, it's very improbable, but they do exist. There exist clusters with very, very many particles. So specifically, it is not a sampling set, not at all. It is not a sampling set. Furthermore, it is also clear that it is not possible from this set to extract a minimal subset. Because in fact, if a set is complete for Bergmann space and you remove one point, it is also complete. There is a difference between, the difference is that a holomorphic function on the disk, if you multiply it by z, it is still holomorphic square integrable function. So it's always possible to remove one point. It's still complete set. So so this set does not admit a minimal subset. Does not admit a minimal subset. So and this is why the question of interpolation, so we have here, the interpolation was just by Lagrange formula. But the question of interpolation here clearly must be different because the values inside don't matter. The only thing that matters is behavior at the boundary. But Bergmann function does not have boundary values. So if we take a function, say from Hardy class, if we take a function that admits boundary values, then of course interpolation from subset, there is no question. Just go to the boundary, find the boundary values, and use the Poisson formula. But Bergmann function does not have boundary values, and still, nevertheless, so we have the following result, interpolation result with, okay, let me go here, maybe. So, interpolation result in joint work with Xu, and it just appeared, so it is from 21 and already published. So, in joint work with Xu, so we have just the following result, that if I use Peterson-Sullivan interpolation, so what do I mean by this? I write summation, I write, if you wish, Poincaré series. Let me write x0. Let me write z0 like this, z0, x, just to stress the difference. Z0 is the position of the observer, and x is my configuration. So over the sum, So D is the Lobachevskian distance. So the Lobachevskian distance. So the S is taken to 1, and S goes to 1 descending. And this gives me f of z0. So this is the result we have for a. So here is the point. This holds for any f in Bergmann space, for any f in Bergmann space, and almost every x. So please observe the order of the quantifiers. So for any f in Bergmann space, the statement holds almost surely for fixed f, for fixed Bergmann f.
Which measure on x?
Excuse me, this one, always the same. The determinantal process with Bergmann kernel, which is, excuse me, yes, I should have written pk, yes, thank you very much. Just x is 0 set of Gaussian analytic function. X is 0 set of Gaussian analytic function. In fact, also we have generally also in higher dimensions, Bergmann space have higher dimensional complex hyperbolic spaces, but just please allow me to stay in one dimension for this talk. But in fact, it holds significantly great generality. Okay, so this is the result. Please observe that it holds for fixed f and almost every x. So it does not hold for almost every x and any f. So this result is not uniform. The 0 set, so the result holds almost surely, it means that a set of measure 0 is being thrown away. The set of measure 0 that is being thrown away depends on the function f. Depends on the function f. In fact, it is very tempting to write, instead of f of x, to write here, to write k x, and to investigate the convergence of this family of reproducing kernels. But it doesn't converge. It does not converge. So this statement is not uniform in f. My intuitive explanation is the following, that, as I said, the Bergmann function can be very wild at the boundary. It does not have boundary values. It can be very wild. And precisely different Bergmann functions are wild at different portions of the boundary. So somehow, this is, as I said, this is just hand-waving explanation. So in throwing away a set of measure 0, I throw away some trajectories, some realizations which approximate that part where the Bergmann function is bad. But precisely, it is not possible to satisfy all Bergmann functions simultaneously. So in fact, I should say summation here is also in principal value, namely over annuli. Over annuli. So precisely, for fixed Bergmann function, I have that these sums over annuli, they converge. But for all Bergmann, uniformly, it's simply not true. We show that it's not true. So it is not only that we do not, this interpolation procedure does not work uniformly, but in fact, we show that no interpolation procedure can possibly work uniformly. So in fact, there does not exist a uniform version of this result unless I were to go, so let us see. We do have, but only in the case when, so let's see, for example, the Bergmann kernel, it is sum of k plus 1 z to the k, w bar to the k. So if I take just the sum of z w bar to the k, I get Hardy space, and of course there I have values. Uniform can go a little bit beyond. Go if here I put logarithm k. So if I have reproducing kernel space, subspace of Bergmann space with logarithm of with logarithmic decay of norms, then it's okay. It still does not have boundary values, but have this uniform convergence. And I should say, still it is not clear. It is not clear if it is possible to have some uniform procedure. So it is a uniqueness set, but it is not clear if it is possible to have uniform procedure of recovering Bergmann function from its values on these realizations. Please observe at the same time that this Patterson-Sullivan formula, this formula is, in fact, does neglect the compact part. So the formula only takes into account the boundary behavior of the function. So all the values in compact part are thrown away. The end result does not depend on them. So in that sense, it is quite, how shall I say? It is compatible with the problem, with what the problem asks for. So in some, so I have space. So I have Bergmann space. So I have very small subspace, which is Hardy space. So, but I have intermediate subspaces, which are smaller than Bergmann, but bigger than Hardy, which do not admit boundary values, but for which this holds. So, and we have specific conditions. So the coefficients need to have logarithmic growth. Yes, of course, but for Hardy space, there is nothing to prove because this Hardy space has value, so just can take, so a much simpler interpolation formula works, just take boundary values and use Poisson formula. Okay? Okay. So if, so this much for the formulation of results, and if there are no questions at this point, maybe I would like to say a few words about the proof of the result for the sign process. So a proof of the result for the sign process. Okay, so we leave the Bergmann kernels completely. So, and I go to the proof for the sign process. So, and the first step in the proof, so I need the scaling limit of the Borodino-Konьков-Geronimo case formula. So the scaling, okay, so the scaling limit. So proof for the sign process, proof for the sign process. So let me just say that the convention I use for the Fourier transform is the following. Okay, so just, okay, so let me just have the following. I would like to, given a function h, I would like to assign to it continual analog of continual Hankel operator. So, okay, so just and the scaling limit of, so scaling limit of Borodino-Konьков-Geronimo case formula. scaling limit of Borodino-Konnikov-Geronimo case is the following. So just, I want to have an estimate for expectation of multiplicative functional under the sign process. So here, as usually, I write f equals f plus plus f minus. So where f plus, the Fourier support of f plus is on the positive half line and the Fourier support of f minus is on the negative half line. I don't need f to be real valued. So in fact, I need this lambda. Let's write e to the f, excuse me. E to the f, I will need it a little bit later, but okay. So this is clearly the exponential of the integral of f plus the Sobolev 1/2 inner product, the Sobolev 1/2 inner product. So let me write that the Sobolev 1/2 semi-norm is just the integral, this one. Okay. Okay, and so f by f tilde, I follow the standard conventions that f tilde means just swapping the Fourier transform. Swapping the Fourier transform. Okay, and then there is precisely the correction term of Borodino-Konnikov-Geronimo case, which will be just, so I need, excuse me, I need a lot of notation here. So I need h. H is the exponential of f minus minus f plus. F minus minus f plus. So, and I need h at 2 pi. I need the following scaling. So, okay. So determinant 1 minus characteristic function from 1 to infinity h to pi. So, yes, so here we go. Okay, so the 2 pi factors, appear a little bit because precisely when one takes scaling limit and passes from, so especially with this for the from Fourier series to Fourier transforms, there are 2 pi. So, okay, so there we go. I should say that this is just straightforward exercise of taking scaling limit in the Borodino-Konnikov formula. Just write the Borodino-Konnikov formula and take scaling limit. But in this form, I have not seen it written down. So I was looking for somebody to quote, but maybe the experts should tell me, but I have not seen it written down in such specific form, even though it is just a 3-line exercise. Okay, so my point is that this statement shows, in fact, that multiplicative functional, so what is this? This is expectation under the sign process of multiplicative functional. So let me write it like this. Exponential of an additive functional. Exponential of an additive functional. So, okay, let me continue here. Exponential of an additive functional. So I just so additive functional is just sum of particles, sum of values of a function over particles. I have 5 minutes, I believe, right? Yes. So it is sum of values of function over particles. So again, what is my aim? What is my aim? I'm investigating the function gx over, so gx of t, here it is. The scaling limit of the characteristic polynomial. The scaling limit. Of course, I take the logarithm, and instead of multiplicative functional, I consider additive functional. It is convenient for me to regularize, to shift, to consider product x, but to shift x to write something like x plus I, something like this, in order to have Sobolev functions belonging to the Sobolev space. This doesn't change the situation for my purposes. So I can consider normalized, or if you wish, considering t not real, but with imaginary part 1. So I have these of such additive functional is log t. One can compute it. So there is, in fact, the central limit theorem. By the way, this formula allows one to give estimate on the speed of convergence in the central limit theorem of Soshnikov. And there seems to be a very significant difference between the behavior for finite n, where Johansson obtained very, very fast convergence, super exponential, very, very fast. But in this situation, so at least using naive estimate, so estimating determinant by trace and so on, one gets very slow rate of convergence. Very slow rate of convergence. So if f is homothetized by coefficient r, the rate of convergence I get is constant over logarithm of r, as opposed to these exponentials of Johansson. So there does seem to be a difference. So this scaling limit, this, how shall I say, correction term to normality is significant term. At least if it is not, I don't know how to see that it is not. I only have estimates which show that it converges to 1 very slowly. Okay, but in any event, the logarithm of this quantity for t has variance log t. So there is a probability for such random variable, there is a probability of large deviations. Probability that this random variable is not as large as square root of its variance, but as large as its variance. These probabilities can be computed, and the series diverges. So one would like to use the inverse Borel-Cantel lemma and say that clearly the event that there are many enough of these events, this event has probability 1. So the problem is that they are not independent. They're not independent. They have, one can compute their correlation, covariances, and everything. Here it is. So one can compute. So one can approximate this by Gaussian process. And again, for Gaussian process, one can prove the result that we want. But then there is a question about, so we are interested in event where a random variable is very large. So the fact that a random variable converges to a Gaussian random variable, it's not the same as saying that the tails also have Gaussian behavior. I need a rather sharp estimate on the tails of these random variables. And please observe that now I put lambda here. If I put lambda here, so I'm interested in characteristic function, so lambda is imaginary, then here it becomes real. So this is exponentially, this becomes exponentially large, this explodes. So at least from this formula, I cannot, so for lambda real, this quantity is 1, there is no doubt about that. But for lambda imaginary, when I want decay of characteristic function, so for approximating my random variables by Gaussian random variables, I need decay of characteristic function. And decay of characteristic function, for large lambda precisely in order to evaluate the Kolmogorov-Smirnov distance between my random variable and the Gaussian random variable, because this is what would allow me to have an estimate on decay of tails. Decay of tails. In fact, I don't consider exactly the Kolmogorov-Smirnov distance, but a little bit smoothed. But the point is that I do need this distance to be sufficiently small in order to have estimate on tails. Otherwise, I cannot have estimate on tails. So, and here, since I cannot use this formula, I use a very beautiful idea of Johansson, namely the idea of change of variable. So instead of considering, well, I mean, it is an old idea that just if to replace oscillating integral by exponentially decaying integral. So I change contour of integration, and I use precisely change of variable formula. And here there is a difference in explaining which I will finish. So Johansson, in working with unitary group, also changes contour of integration. There is contribution coming from the Jacobian of change of variable. So the square of van der Monde, the determinant on the contour and on the shifted contour. And for Johansson, this contribution is negligible. Change of variable is done in such a way that it is negligible. But this is not the case here. So in this case, it makes an important contribution, at least, okay, let me say, my estimates don't allow me to prove that it is negligible. And the key point precisely, is that it is possible to do such change of variable. So in fact, and here with this I finish my talk. So in fact, the sign process is quasi-invariant under the action of the group of diffeomorphisms of compact support, and just let me write this. So if I have my sign process, so quasi-symmetries, of the sign process. Again, I should say I stick to sign process, but these results have analog also for Airy, Bessel, and so on. So just sign process, post-composed with a diffeomorphism. In fact, is equivalent, it's an equivalent measure to the initial measure. And the Radon-Nikodym derivative is the following multiplicative functional over pairs of particles. Multiplicative functional over pairs of particles, here it is. And just, it is possible to give sense to this expression and so on, and to estimate the moment and so on. So, and also, if f is now not exactly diffeomorphism, but a shift of the contour, it is also possible to write such multiplicative functional and to estimate it. And estimating, it is possible to do the change of variable formula in the spirit of Johansson, and then it is possible to reduce the exponential function, the fast oscillating characteristic function, to replace it by rapidly decaying exponential function. And then one uses, in fact, the decay just comes from the as in fact also in Johansson case, comes from the very first term in the Séguin theorem, and this allows to obtain the desired estimate on characteristic functions and the desired approximation of the distribution by the normal distribution and the desired probability 1 of these high fluctuations, and the main result that the sign process without one particle is complete and minimal. The realization of sign process without one particle is a complete and minimal set for the Pelley-Wiener space. Thank you very much.
Questions? Let me know if I give you a microphone. Any questions? Okay. Is there no more questions? So let's reconvene at 11:40 in 10 minutes. Okay. And thank you again.